starting on time. I'm in shock. Okay. And a great day to do it because of how much I want to get through on finite difference methods. Okay. So we focus on specific PDE. Last time we saw stencils, so finite difference formulas for certain derivatives. So now we'll make use of those to solve a particular initial boundary value problem. So what we have here is minus 2x of f on the interval 0 to 1. And I'm going to gloss over the fact that even though this is a class about numerical methods for PDEs, that this is technically an ODE. But what I'm going to show you here can be applied to PDEs. For instance, we took this problem from 1 dimension to 2 dimensions, and that would be a PDE. At the left boundary, we have this condition, u of 0 is equal to a, so this is a Dirichlet boundary condition. And then at the right endpoint, x equals 1, we have du dx is equal to the value c, that is a Neumann boundary condition. So I can illustrate the very different ways in handling those conditions. Okay. All right. Now, what we're going to do is discretization. When I take this differential equation, which is dealing with a function defined on a continuum, and come up with a set of equations that will produce an approximate solution at selected points, a discrete set of points. So that's what I mean by discretization, where our domain is going to change from a continuum, the interval 0 to 1, to a discrete set, a grid of points from the interval 0 to 1. Okay. Now, so the way I'm going to define my grid is I'm going to have a certain number of interior points, x1 up to xn, and I'll define x0 to be 0 for left endpoint, and then xn plus 1 will be the right endpoint of 1. And we have a formula for each grid point. It's the index I times the spacing h equal spacing, so it's just the length of the interval divided by n plus 1. So if you have n interior points, spacing has to be 1 over n plus 1. Okay. Okay. Now, I'm actually going to need, so even though this is our domain, 0 to 1, so we should only be concerned with points here, we actually are going to need one more point outside. So this would be xn plus 2 that has the same spacing. That's because of the Neumann boundary condition. So this is what's referred to as a ghost point. It's really just an abstraction for the purpose of designing the scheme that we will use to compute a solution at these points that are, and this one also, are non-ghost points. But but having this point around will still be helpful to us. Okay. All right. Okay. And then I'm going to define U sub I to be our approximation to the exact solution at xi. So just a notational convenience. So our goal is to compute U1, U2, and so on, up to UN plus 1. So we try to compute solution at all of these points, everything in the interior, and also this right boundary point. How come I did not include in that the U0, the value of U at the left boundary? How come I did not need to do that?
That's the boundary function.
Yeah, we already know what it is. So make a note here that U0 is already known to be A. So whenever you have a Dirichlet condition imposed, the solution's already known at that point, and you focus on computing solution at all the other points. Okay, whereas here, a Neumann boundary condition specifies only the derivative at this point, not the value. So we still need to try to get that. Okay. Questions at this point? So the idea is to get from the PDE to equations that we can solve to get these U values. And since the PDE itself, in this case, is linear, the equations themselves will also be linear, or it should be. So, in other words, we're going to go from this PDE to a system of linear equations, an AX equals B problem. And we know how to solve that. You're all in 610. Well, didn't even need 610. It's a lower level thing. Okay, so how are we going to get those equations? That's what these finite difference stencils are for. So we have minus U XX at a given point xi is equal to f of xi. So this is just evaluating the PDE at a certain grid point. So now I'm going to replace uxx by a finite difference formula. Well, uxx is known to be equal to ui plus 1 minus 2ui plus actually ui minus 1 over here, ui plus 1 over here. Just have things in order from left to right, over the spacing h squared, plus error, that's order h squared. So this is what we saw last time. The center difference for second derivative is that. So this is an equality. So second derivative is equal to this approximation plus this error. And that is equal to fi, which is defined to be f of xi. Now, everything I've written here so far is exact, but what we're going to end up with is just an approximation. We're only going to be able to solve for u approximately. So we neglect this, and our system of equations will come from that. So because I'm neglecting this, that's why we're only going to get an approximate solution. And these equations hold for I equals 1 to up to n plus 1. Okay, so we have n plus 1 equations in n plus 1 unknowns. That's our goal. Okay. All right, so this is the Now, the ideal thing is that we can just go ahead and write out these equations, describe it as an AX equals B problem, like figure out what is the matrix, right-hand side and all that. But we have one complication to overcome first. And that is, if I were to write this out for I equals 1, 2, up to n plus 1, yes, we're going to have our unknowns that we're trying to get, but we're going to have other things too, and we have to deal with them. So, so there are three cases to consider. Interior cases that do not deal with a boundary in any way. So I equals 2 up to n. These are the easy ones. So in that case, I would just have exactly what I've written here. Okay. Now, what points am I referencing? UI minus 1, and UI plus 1. But all of those points are among our unknowns, U1 up to UN plus 1. So those equations are perfectly fine just the way they are, because they do not involve any boundary points. The next case is not too big a deal. The left boundary. That's for I equals 1. So if I fill in I equals 1 in here, I'll have minus, then I have U0 minus 2U1 plus U2 all over H squared is equal to F1. But we know what U0 is. U0 is equal to A. So we just go ahead and fill that in. But I want to write these equations so that all terms involving the unknowns are on one side, all other terms on the other side. Why? Because that's how we write it as a system of linear equations, AX equals B. Because like if you're solving this in MATLAB, for instance, or whatever software, what you want to do is have matrix times unknowns is equal to right-hand side, and then you solve that by whatever software, like using MATLAB's backslash, for instance, or writing your own routine. So I'm just going to rearrange this. So we're going to have minus, and then everything else in here is equal to F1 plus A over H squared. Okay, so in other words, your right-hand side of your system of equations is normally just F. But for the first equation, for I equals 1, we have this extra term that comes from a boundary condition. So any questions about this before we deal with the other boundary condition? By the way, you might find it strange that we have minus UXX is equal to F, because F can be anything. I could have said like UXX equal to minus F, or replace F with minus F. And I've carried this minus throughout. The reason why Poisson's equation is conventionally written with a minus is because the Laplacian has negative eigenvalues. As an example, one dimension, you have sine x. Well, second derivative is minus sine x. So sine x is the eigenfunction of Laplacian with an eigenvalue of -1. So by putting a minus, the differential operator minus Laplacian has positive eigenvalues. This would lead to having a system of equations where our AX equals B problem, matrix A will be symmetric, positive, definite. And as you know from 610, there are certain methods of solving system linear equations that are designed for symmetric, positive, definite matrices. It's a favorable situation. So that's the only reason why that minus is conventionally put there. Okay. So now we need to deal with a right boundary. I is equal to n plus 1. So we put I equal n plus 1 in here, and we'll see what we get. Okay. Okay. So I have minus, and I have un minus 2un plus 1 plus un plus 2 all over h squared is equal to f n plus 1. So we have a problem here that this is not among our unknowns. Also, we don't have a value for it. We can't just stick a value in there like we could for a Dirichlet boundary condition. So we need to make use of the Neumann boundary condition. So if we discretize the Neumann boundary condition, du dx at 1 is equal to c. Here's how that can go. Because 1, recall, is equal to xn plus 1. So we're approximating a derivative at that point. Well, we can use that, we can approximate a derivative using neighboring points. So we get un plus 2 minus un over 2h, which is an approximation of du dx at xn plus 1, and that is equal to c. Now, what's very important here is this is second order accurate. Very important to use a approximation to du dx at the boundary that has at least the same order of accuracy as the approximation of any other derivatives in the interior. Because we're using a second order accurate approximation of uxx from the PDE. If I had used like a forward difference here, that's first order accurate, it would ruin the solution everywhere. In other words, it would make the whole solution first order accurate. You must use approximations of a consistent order of accuracy throughout your discretization. So that's why I'm using second order here. So here's once again the centered difference, but for first derivative. Okay. Now, the nice thing about this is now I can solve this equation and get a value for un plus 2. So un plus 2 is equal to 2hc, okay, is equal to un plus 2hc. That gives me a way to eliminate un plus 2 from that equation. I can just substitute that in there. Now, it does involve un, but un is something I'm solving for. I'm perfectly fine with having un as part of this. So once I simplify as much as I can, so I'm going to have two un minus 2un plus 1 plus 2hc all over h squared is equal to fn plus 1. Okay. And then what I can do is I want to write everything so that only terms involving unknowns are on the left side, everything else on the right side. So I'll just rearrange. So now I have minus 2un minus 2un plus 1 over h squared is equal to fn plus 1 plus 2c over h. So this is my equation for the last row, for I equals n plus 1. Right. So now we have our full set of equations. All the rows. So now I just have to put everything together into a system, equations of form AX equals B. Are there any questions up to this point before I do that? Okay. So the way this works is, okay, so I need to keep that equation here. I'll take a picture. Okay. All right. So I'll leave the boundary equations up because those are the more interesting ones. Okay. So to obtain our unknowns, u1, u2, up to un plus 1, we're going to solve the system a u is equal to f. Now, I'll write out in full what that is. Now, the vector u, just consists of our unknowns, u1, u2, un plus 1. And then our vector f, well, first element is this one, f1 plus a over h squared. And then after that we have f2, f3, and so on, just f values only, until the last one is also an extra term, plus 2c over h. So that's our right-hand side, just lifted from the equations I've written out before. Now to fill in the matrix, we take whatever is multiplying the u values. Now, for all the equations in the interior, we had the center difference approximation. So that's going to have 1 over h squared, I'll pull out front, 2's down the diagonal, and then minus 1's to the left and right. Okay. So that handles everything except for the first and last rows. And that just comes from this. I've applied the minus to negate everything. So any questions about where the interior rows come from before I do the boundary rows? It's just the multiples of the u's. Because for each equation, the equation number I, we have 2 times ui. Now, the index within an equation is a column index. The index of the equation itself, the row index. So that's how we fill in the rows and columns of this matrix. Because we have, in equation I, we have a minus ui plus 1. That's why we have this in column I plus 1, and also column I minus 1. It's the same. So, who can tell me what should go in the first row of a matrix from this equation right here? Almost.
What was the question?
Okay, what entry should go in this row? So we're dealing with this equation. Whatever is multiplying our unknowns goes in the matrix.
So are we just looking at the first? We want one position or everything in that row?
Well, normally look at everything except that there's only select terms in the equation. So any unknowns that are not featured in the equation, those entries will be 0. So yeah, we're only going to have a very few non-zero entries. Robert?
Would be negative 2 and 1.
Almost. Look again really, really closely at that equation.
Okay, so that should be 2 and negative 1.
Yeah,
It's got to be negative.
that's minus.
5.
Okay, yeah. And it's a logical continuation of what we had in the upper rows. I mean, we have this term falling off the edge, but it wound up over here. Okay, so that's the first row. We all see how that came about. All right. And then, okay, last row. So corresponding to I equals n plus 1.
2, 2, negative 1.
There will only be 2 entries.
Oh, yeah. I thought that plus 1 was, I'm sorry, negative 2 and 2.
Yes. So the 2 we've had done on the going down the diagonal will remain a 2. That's a coefficient of un plus 1. Minus becomes a plus. And then, yeah, we have a minus 2 over there. You can almost think of it as these 2 getting added together to make that, which came from applying the Neumann boundary condition. Okay, and now we have a system of equations. Any questions about that? Okay. So all these entries are the coefficients of uj in equation I. That's where that's also it's a rigorous definition of where the entries come from. And each equation involved at most 3 unknowns. So that's why we have at most 3 non-zero entries in each row. So what's nice is it's typical when using finite difference methods, we have a sparse matrix. Most of the entries are 0. Now, we could just go ahead and solve this by various methods. Well, what would be an example of a method we could use to solve this? From right here, 610.
This is not symmetric question.
Yeah, it is not. It is not symmetric, which is unfortunate. So we can't use methods for those kind of systems. What can we use instead? Yeah, you could use GMRES if you want an iterative method. If you're going to use a direct method, what would that be?
LU?
Yeah, this is Gaussian elimination, which produces the LU decomposition. Okay, so we could do that. However, what's preferable is to make a slight change to this system. And a very simple change. What I'm going to do is I'm going to take the last row, only the last row, and divide through by 2. So, and then I have to divide the right-hand side by 2. So the system is equivalent. What did that buy me? What's the benefit of doing that?
So you say that again, you divided by what?
I divided the last row by 2. And this is what I have. So, what's the advantage of doing that, of having this matrix instead of the other one? What property does this matrix have that the other one didn't? It's symmetric.
Is it though?
Yeah, now the diagonal never matters for determining symmetry. It's only the off-diagonal entries that matter.
Oh, really?
Yeah, because, well, okay, we should not have an imaginary part, but I made these 2 off-diagonal entries equal. So yeah, so mirror image off-diagonal entries must be equal. The diagonal can be whatever it wants. So yeah, so this is for symmetry. And although it'd be difficult to prove, and I believe I had done this numerically for example, that this matrix is not only symmetric, but it is also positive definitely. Well, being symmetric, it'll have real eigenvalues. The eigenvalues turn out to be positive. So now, what methods are on the table that were not before? Like, give me one direct method and one iterative method.
Well, direct is could use Truncation.
Yep.
Indirect could use approximation, could use conjugate gradient.
Conjugate gradient. Well, You would know better than anybody in this room. So, yeah. So you can use Cholesky, which would save half the operations compared to Gauss elimination, or conjugate gradient, which is particularly effective for most systems, although some sort of preconditioning would probably be in order. Yeah, so sometimes a little change like that can actually reduce the number of operations needed to solve the system. So when symmetry is possible, it's good to pursue it. Okay.
Yes. Oh, never mind.
Okay. All right, it's totally break time.
Anybody watching any good show?
I just started Grace and Frankie. Have you watched
Oh
that?
my god, I
Yeah.
love that.
I don't know how long
That
it's
is
been
so
out. Like, I've just been missing out, I think, because I saw it was old ladies, and I was like, nah.
But then I watched the trailer and I was like,
Oh, that's funny.
exactly, yeah, I think it was just this year, like I just finished the new season not long ago at all.
But there's like 7. It's like, holy cannoli.
I'm like absolutely in love with Frankie.
Yes, same.
Goals.
Yeah, I haven't been watching much of anything. There's like 2 animes I've been keeping up with that. Besides that, I need to watch the season of Lucifer that just came out.
Is that show pretty good?
It is.
I'm looking for like a recommendation because well, right now I'm watching The Last OG, which is like hilarious, by the way, but I'm on season 2 out of 2, so I need something else.
I enjoy Lucifer at least. I know some other people who really enjoy it.
What's the plot?
So, are you familiar with comics?
Am I familiar with comics? No.
Okay, I was going to say if you are, then it's a loose adaptation of the Lucifer Morningstar character from DC Comics. But basically, Lucifer is living in New York City working, and he owns a nightclub and he's working as a detective.
Is his name just Lucifer, or is it like?
Robert, I need to interrupt you. He is not living in New York. He lives in California. He lives in the city of Angels.
I did not know. That is interesting. Would you say it's like dramatics, or does it have any comedy, I guess? No? Yeah, no.
Some, not a lot, but it does have some.
Okay, that's fair. That's fair. I think I'll try that next.
Lucifer is a really funny show at times, too.
Since you brought that up, Brooklyn Nine-Nine.
That is good. I haven't watched the new season. I think it's gonna be the last season too.
It is.
I really like Terry Crews. He's a giant
I
teddy
love
bear.
Terry Crews, but
Yeah, he's good.
I cannot see Terry Crews in anything without thinking about his role in the movie White Chicks.
Yeah, that carries him around. That's funny. I mean, followers. And then I had a big crush on, oh my goodness, his name is in my mind. Andy Blankberg is what's in my mind.
Oh, Andy Samberg.
Thank you, Sand. So, yeah, I gotta, yeah, when I'm supposed to be doing other stuff, I've been doing this.
That's cool, like,
Well, basically, I was just like drawing a bunch of 3D shapes and coloring them. So,
Well, it looks
thank
like-
you.
that's really impressive.
Wow, I didn't realize that. Thank you. It's really just been like, I don't want to do my real work right now, so I'm coloring.
Like, I'm actually wow. Like,
Oh, well, thank you. Don't look at it too long, it'll look worse. Start noticing the flaws. What class is that next door?
I think that's modern algebra.
So that would have like juniors and sophomores, wouldn't it? No, no sophomores.
Probably junior, at least juniors.
Okay.
I'm not sure if there's any graduate students taking it this semester or not.
Okay, I'm trying to advertise for McNair, so I'm looking for like sophomore courses or.
Okay.
like, Dr. Chen's the science goes in it. Robert, like, you get Dr. Chen's in it? I feel like maybe we should set it to just send. Every Monday and Wednesday, just,
Probably.
Oh, the COS 703
yeah,
X instructor.
You're
yeah.
still getting emails from
Still
her.
getting,
Yeah.
Like, you need assistance with your assignments, join my meeting this Wednesday. But she's no longer the instructor for the class.
Is she an instructor for any class now?
I don't know.
I looked, I only saw like topics classes and so forth, like not a regular class, which is best for all concerned. But yeah, because it's something, you get the emails like, and like, makes you wonder, like, was it only a dream that the professor got changed? And
Yeah.
you're just stuck like, oh, I'll never escape this. I just wonder, like, what else can I make happen by emailing Dr. Schroeder? I don't know if that was what caused it, but you have to wonder.
Get these guys a raise.
What?
Get these guys a raise.
I mean, I wouldn't complain.
Okay, now, so now that we have, at least for this case, example of Poisson's equation, a numerical method that produces an approximate solution, what we'd like to know is, as the spacing, the grid spacing h goes to 0, does the numerical solution converge to the exact solution? It'd be nice if we could prove that. That would give some confidence in the use of numerical methods. And that's important because, for example, back in the 50s or so, when we first started to have electronic computers, Gaussian elimination has been around for a long time. But when it was implemented on electronic computers, there's this issue of round-off error. And people seriously begin to wonder, is Gaussian elimination unstable? And some people actually believe that it was. And that would have been a big problem because now we finally had something that can perform computations automatically and a method to carry them out. And what if the method could not be used because of round-off error? So that's when Jim Wilkinson performed a very careful round-off error analysis and proved that Gaussian elimination actually is stable. And that's why it continues to be used today. If it wasn't, then they would have had to maybe rely exclusively on iterative methods. So that's why this theory like that is so important. Okay, so we have a PDE. My notes here, I don't have a minus. I'm going to keep a minus in, just for consistency. It is approximated by the system linear equations I just came up with, AU equals F. So I'm going to let find U hat to be equal to U of x1, U of x2, so forth. Okay. All right. Where in this case, this refers to the exact solution. Now, I want to emphasize this notational convention. When it's U of X, that's in discussion of numerical methods, that refers to the exact solution evaluated at whatever point. U with a subscript refers to the approximation, the computed solution. Okay. So we solve a system of equations, and we get this vector U. That's our computed solution. We want to compare this to U hat, which is the exact solution evaluated at the same points. Okay. So I'm going to define a very important concept in error analysis, the local truncation error. abbreviated LTE. And so that's the vector tau. And it's equal to A times U hat minus F. Now, that's my formal definition of local truncation error for this problem. Now I'm going to give the informal definition that can be applied to all kinds of problems. Boy, that's rain out there. Ugh. Okay. Local truncation error for not just this problem, but whatever problem is obtained by substituting the exact solution into the numerical method. So for all different kinds of differential equations, there's the Alvarado notion of local truncation error, but it's all unified by this one concept. Okay. Because if I substituted a computed solution in here, well, that's the solution of AU equals F. I'd get 0 for this. But I'm not substituting the computed solution, I'm substituting the exact solution. So it's not going to satisfy the system of equations exactly. There is going to be some error involved, and that's what tau is. This expression you may also recognize as the residual, although residual is customarily defined the other way, like F minus AU. But either way, you're substituting the exact solution into the numerical scheme. Now, for this particular problem, we get a handle on what the local truncation error looks like. So each element of tau comes from the center difference approximation. Let's see, so it's minus, okay, so I need a -1 here. Okay. Minus F of xi. Okay. But because it is a center difference approximation, we know that this is equal to minus uxx at xi. And some error. So the error term in this case is so minus 112 fourth derivative of u at same point, h squared is a second order accurate approximation. And then there'll be additional error terms that are order h to the fourth. Okay, minus f of xi. Okay. Now, but the thing is, u is the exact solution. Minus uxx is equal to f. Since it equals f of xi, these terms cancel. So what we can see is that the local truncation error is order h squared. So because of this, the scheme is second order accurate. And at least locally, the local truncation error is of that magnitude. That is one notion of error, local truncation error. But it's not the most important notion of error we need. It's actually the easiest one to work with. The real error we care about, the global truncation error. So GTE is E, vector E, which is equal to U minus U hat. That's what we want to be small. That's the actual error in the solution. Now, what I'm going to do is multiply both sides of this equation by A, matrix A. So AE is equal to AU minus AU hat, but AU is equal to F. So now I have F minus AU, whoops, that should be a hat. So now I have F minus AU hat, which is this, except with a minus. So this is very important. It relates the local truncation error to the global truncation error. So you can think of a global error as being kind of like the solution to the same PDE that we've been solving, except the local truncation error is the right-hand side instead of F. And if you were to solve this, you would find that E is also order h squared. By integration. Okay. All right. Now, the global truncation error is what we care about. The local truncation error is easier to get. Kind of like when covering error analysis in Math 46560. Forward error is what we care about. That's what global error is in this case. But backward error is what's easier to get. It allows us to estimate the error that we really want. Questions up to this point? Okay. So, the thing we need to be careful about is, suppose we compute a local truncation error, and we see that as h goes to 0, the local truncation error goes to 0. How do we know whether the global truncation error also goes to 0 as h goes to 0? We have to be sure of that. And if we can determine when that's going to happen, then that'll be ideal. Then we can just find the local truncation error. Okay. So suppose the local truncation error goes to 0. That means it goes to 0. Does the global truncation error go to 0? Well, that is not a sure thing. You like to know when it does and when it doesn't. So for this problem, we can use the relationship I just derived between local and global truncation error. So global truncation error is equal to minus A inverse times the local truncation error. So if I take norms of both sides, so whatever norm I choose, the norm of the global truncation error is less than or equal to the norm of A inverse times the norm of the local truncation error. So here's the problem. Is this bounded? What if, as h is going to 0, okay, this is getting smaller. What if this is getting larger? That's a problem. Then we cannot be assured that this is going to 0 too. And this leads to the concept, a very important concept of stability. So, I'm going to pay attention to time here, okay. I think I can pull this off. So our finite difference method for this problem is said to be stable if the norm of A inverse is less than or equal to some constant C for spacing h that's sufficiently small. Now, I'm going to be a little lazy in my notation. The matrix A depends on h, and we saw the matrix A from earlier, Poisson's equation, that we have this finite difference scheme where we're dividing by h squared, so it's a function of h. It denotes actually have a superscript h in here. So because we care about what's happening as h goes to 0. So if as h goes to 0, this is bounded by some constant, and C has to be independent of h, then we have the assurance that we need, that as this goes to 0, this must also go to 0. Okay. Okay. All right. So here's the terminology we need to discuss questions of convergence. So the numerical scheme, and I'll correct my notation here, AH, UH is equal to FH. So here I'm writing the H to make it clear that everything in the system depends on H. Is, okay, consistent if the local truncation error from this spacing h goes to 0 as h goes to 0. So that's if local truncation error behaves the way it should. But what we really care about is the scheme being convergent. And that's the case if the global truncation error goes to 0. as h equals 0. So we want to show the method is convergent. It's just easier to show that it's consistent. But that's why we need the concept of stability. So stability is our bridge from consistency to convergence. So what I'm showing you here is that if the scheme is also stable, based on the definition given there, then it is convergent. And this leads to what's called the lax equivalence theorem. Okay. So, actually, so very quick to state that the scheme is convergent. All right, so the scheme AH/UH is equal to FH is convergent if and only if it is consistent and stable. And you can, so I've already shown you one direction that I've shown you this direction, that if the scheme is consistent and stable, it is convergent, and we just use these properties and norms to see it that way. The other direction I won't get into, that's certainly going to be more difficult. Okay. All right. So questions up to this point? Yes.
Yes, it's probably a silly one, but lax, is that a word or abbreviation? Like,
Okay, I will talk about that. I want to anyway. Any other questions first? Okay. No, Lax is a person. Peter Lax, a professor at NYU. Let me see if he's still alive.
I couldn't help but think Los Angeles Airport, but.
That comes to my mind too. Yes, he's still alive. He's 95 years old. Okay, I've actually seen him when he was, he probably doesn't know who I am, but I've been in the same room with him when he would visit Stanford. And it was amusing because I'd see him at the weekly applied math seminars. So he'd be sitting right there up front, dead asleep, back. Yeah, so that's his right. The other part that's interesting was when he was the one giving a talk. So he'd do it the old-fashioned way, like an overhead projector, have these transparencies. And what I found really odd was a lot of speakers, when they're using overheads and they want to point, they might point directly on the transparency, or they might be using a pointer and point directly in the screen. But not him, no. He would have his finger out somewhere in space at just the right point to whatever he wanted to point at. I think, isn't that a lot harder to do? But yeah.
With the shadow?
Yes. Yeah, he pointed with the shadow of his finger. Like, okay, and it's kind of, these are the things I remember about him, but there's so many things named after him. There's the Lax-Friedrich finite difference scheme, Lax-Wendorf finite difference scheme. There's other versions of a Lax equivalence theorem for other equations. And sometimes there's different people's names attached to it, like the Lax-Richtmeier theorem or Lax-Richtmeier-Morton equivalence theorem. And so I always wonder when you have other names involved, like what role do they actually play? Like, for instance, did Lax play a role in the Lax-Richtmeier theorem, or was it just Richtmeier picking up from where Lax left off? I don't know. Like, for instance, multi-step methods. You have Adams-Bashforth explicit methods and Adams-Moulton implicit methods. Well, the latter were invented only by Moulton using ideas from Adams and Bashforth, so he put Adams in there. Not sure why he shut out Bashforth, but whatever. So Newton-Cotes integration rules are actually due to Cotes. But I guess it must use ideas from Newton. So it's funny, but most serious mathematicians get their names on everything, even if they didn't do it. Like Gauss elimination. Gauss did not invent Gauss elimination. That was around long before him. So yeah, that's my dirt on Peter Lax. Okay. Now, what we don't know yet from the scheme we've been dealing with for Poisson's equation, we don't know if it's stable. I haven't shown that. And I have 4 minutes to show that. The 2 norm of the matrix A, when it's made symmetric, that's very important, is the spectral radius of a matrix. Spectral radius is defined to be the absolute value of the largest eigenvalue. But that would be 1 over the minimum eigenvalue of the original matrix. So if we can show that this is bounded independently of h, as h goes to 0, then we're good. Then we can say that the scheme is stable. Fortunately, in this case, we do know the eigenvalues. Oh, you know what? The eigenvalue formula running here applies to the case where you have Dirichlet boundary conditions at both ends. The formula would approximately apply with the Neumann boundary condition at the right end, like we have. So this is Dirichlet only. Okay. Now, using a Taylor expansion, you can actually show that this is equal to minus p squared h squared plus order h squared. So, okay. P is a positive integer. So, in other words, the eigenvalues do not go to 0. The matrix is not singular, but the point is the eigenvalues are bounded from below an absolute value independently of h. So if I take 1 over this, I'm going to get something that is bounded independently of h. So this tells us that the norm of AH inverse is approximately 1 over 1 over pi squared. So since it's bounded independently of h, the scheme is stable. Now, at least the thing is, this analysis is not always so straightforward. Like for a more complicated PDE, you might have a much harder time proving stability. And something I've experienced personally, how difficult it can be for my own methods. But this is a general idea that any knowledge of the eigenvalues of the matrix you're dealing with can be very helpful to bound a norm, in this case, bound a norm of the inverse. Okay, so the finite scheme that I've shown you today is consistent, is stable, therefore it's convergent. Okay, questions? Oh, I just ran out of time. Next week we get to one of my favorite topics, spectral methods. But then I'll see how everybody's doing on the homework at that point. It is possible to continue with the homework like into problem 2. Actually, I think the rest of the assignments about, the rest of homework 1 is about finite difference methods. Still a pain in the butt, but I'll be sure to make time to talk about those problems. And I know maybe still working on problem 1, so talk about that too as needed. Okay.
Thank you. If we did like a cookout for Saya, would any of you guys go? Oh, yeah.
Oh.
Has anyone driven through Laurel? Yes.
Yes.
Have you seen all the Sanderson Farms trucks? Yeah. No. I just so happened to drive through Laurel this weekend, and that was my first time seeing like how they transport chickens.
Oh, yeah,
It's so bad. I was like, wow, I'm actually like, don't know if I'm gonna eat chicken for a while.
I was actually about to make a joke. Our cookout would be fully vegan, so you're.
I actually really like tofu, so.
Yeah, it's really.
Well, Diana would love it anyway, but.
I mean, tofu is good if you know how to